And here we go. We get to finally the good one, the real spectral theorem. And so this is, I guess, real in the sense of over the reals and real in the sense of the one that really matters. So this is exactly the same statement as it was in the complex case, except for these two parts that I have done in red just to highlight the difference between them. So okay, let's go ahead and prove this sucker. So just as in the complex case, the equivalence of B and C requires no work because it's already done. So once again, this is 541 with just the requirement orthonormal having been added in. So no need to prove anything there. Okay, so now for C implies A. Suppose we take A to be the matrix of T with respect to some basis, or O and B here. And suppose it's diagonal. So then the conjugate transpose of A is going to equal A itself, since it's diagonal, and since we're in the real case here, we don't have to actually worry about the conjugates. So maybe it's enough to say say that, and then we have that the adjoint of T is going to be T itself. Okay, so that gives us one direction. Now for the other direction, let's see, now we're going to go by induction on the dimension. And I should say that there's an analog of this result that holds in the infinite dimensional case as well. Of course, you wouldn't be able to prove that by induction on the dimension, so it takes some further work, but we're not going to go there. So, basis case. Suppose that the dimension of V is equal to 1. All right, so then B is just true in any case, right? So if V has dimension 1, then you take a vector in there, and either T sends it to 0 or it sends it to a non-zero scalar multiple of itself, and either way you have an eigenvector. So the end. So okay, so now let's say let's take the dimension of V to be strictly greater than 1. And suppose, as our induction hypothesis, that the implication we're looking at holds for any inner product space of smaller dimension. Okay, so now let's see. So we are going, A implies C, so we have that T star is equal to T. All right, well, then T has an eigenvalue because we just proved it. That was what 7.27 was all about. So suppose U is such that TU is equal to lambda U, and now we can have So u is going to be non-zero, so if we divide it by its norm, then we can assume that u has magnitude 1 without loss of generality. Okay. Let capital U be the span of little u. Okay, so what do we have? Oh, well, then u is T invariant, because it maps u to little u to a scalar multiple of itself. So that whole space is invariant, right? And so since that's invariant, then we know that T restricted to u perp, so the orthogonal complement of span u, is self-adjoint by our previous lemma, part C. Okay, so that means then that the induction hypothesis applies to it, because u perp has dimension strictly less than v. So by the induction hypothesis, u perp has an orthonormal basis of eigenvectors. Of T. Or I guess actually, to be completely legit, we should say that they're eigenvectors of T restricted to u perp, but then these are also, so these are orthonormal vectors, and I guess I should say orthonormal eigenvectors of T. Okay, so they're not a basis because there's not enough of them, right? But then when we throw in this last one that we just got, then we win. So adjoining u to this list completes that orthonormal list into a basis. And we've got it.